welcome to the deep dive. Okay, let's be real. You've got a massive exam on kinematics coming up, probably focusing on rectilinear motion, right?
Yeah, and the study stuff is just, wow. It feels like alphabet soup.
Yeah.
Variables everywhere, calculus looming. It's stressful.
Totally. Like, designed to make your head spin, especially when you're short on time. It feels like a physical threat hanging over you, that word calculus.
It really does. And honestly, when you're actually in the exam, under pressure, trying to solve some problem about a particle moving, the first hurdle is just figuring out what they're even asking.
Exactly. Is it distance? Is it displacement? What does that negative sign on acceleration really mean? It's confusing.
You mess up the setup, not necessarily the math.
Precisely. So that's why we're here. We went through all the typical source materials, the textbooks, the lecture notes, those killer practice problems, and we've boiled it all down.
Okay.
This is your ultimate grade-saving cheat code. We're laser focusing on just the three big conceptual traps, the things that trip almost everyone up.
Just three things.
Just the three core ideas for rectilinear motion. If you can really nail these, understand the difference between these concepts, you're setting yourself up way better. That's the mission today.
Right. But before we hit those traps, let's just quickly set the scene. We're talking about kinematics. What is that, super simply?
Kinematics is actually kind of beautiful in its simplicity, right? It's just studying how things move.
How they move.
Yeah, like their path, their speed, how their speed changes over time. But this is key. We totally ignore why they're moving.
So no forces, no engines, no friction, none of that.
Nope. We don't care. We're just like cosmic traffic controllers just watching the movement itself. Pure description.
Okay. And we're narrowing it down even more today to rectilinear motion.
Which makes it even easier. Rectilinear just means moving along a perfectly straight line. Think like a train on a dead straight track.
So no curves, no spinning.
None. We ignore all rotation. We treat everything, cars, baseballs, whatever, like a tiny little dot, a particle, just sliding along that one straight line.
Okay, so it's a one-dimensional problem. Just x-axis, or maybe just y-axis, but not both at once.
Exactly. That one dimension is the secret sauce. It simplifies everything we're going to talk about. Master the straight line, you've got the foundation.
Okay, straight lines only. That actually brings us right to the first big conceptual hurdle. This one seems simple, but it messes people up constantly. It's about the path versus the result.
Yeah, this is foundational. Let's call it section 1. The path problem, displacement versus distance. Okay.
So to even start talking about movement, you need to make two basic choices first. You need an origin.
The origin. That's just the starting point, like 0 on the number line.
Pretty much, yeah. Your reference point, where you measure everything from. And second, you need a sign convention.
Meaning?
Just deciding which direction is positive and which is negative. Usually for horizontal motion, right is positive, left is negative.
And for vertical, like dropping a ball. Up is typically positive, down is negative. The crucial thing is, once you pick your convention, you got to stick with it for the whole problem. No switching halfway through.
Right, okay. And this matters because position itself is what was the term? A vector quantity.
Exactly. And that's key. A vector isn't just a number. It's a number plus direction. In our simple 1D world, that direction is just the sign. Plus or minus.
So like, if my position is minus 10 meters?
It means you're 10 meters away from the origin, but in the negative direction. So maybe 10 meters to the left or 10 meters down, depending on your setup. The sign carries the meaning. Got it. Okay, so with position defined. Now hit me with the two big ones everyone confuses. Distance versus displacement. All right. Let's start with distance traveled. I like to call this the total walk.
The total walk. Okay, what's its nature?
It's simple. It's the total length of the path you actually covered, like every single step you took. And importantly, it's a scalar quantity.
Scalar.
Yeah.
Meaning just a number, no direction.
Exactly. Just magnitude. And it's always positive. It just keeps adding up. Think of your car's odometer. Doesn't matter if you drive forward or reverse, the miles just keep climbing. Right? Distance only increases.
Okay. Always positive, adds up everything. Got it. Now, displacement.
Displacement is different. This is the straight shot. It's the change in your position.
Change in position.
Yes.
So, like, where you ended up compared to where you started. Precisely. It's always calculated as final position minus initial position. That's it. It measures the net effect of your movement. And since position is a vector...
Displacement is also a vector quantity. It has magnitude and direction, shown by the sign. It could be positive, negative, or even 0.
Okay, hang on. Let me try to process that. Vector, scalar. Can you give me a simple example? Like, if I start at my desk, walk 5 meters across the room to the right, then turn around and walk 5 meters back to my desk, what are my numbers?
Great example. So you walked 5 meters right, then 5 meters left.
Yeah.
Your distance traveled, the total walk, is 5 meters plus 5 meters. That's 10 meters total. Your legs did 10 meters of work.
Okay, makes sense. Odometer went up by 10.
But your displacement, the straight shot, is your final position, back at your desk, the origin, let's see COG meters, minus your initial position at your desk, 0 meters.
So 0 minus 0.
Yep. Your displacement is 0 meters. Even though you walked 10 meters, you ended up right back where you started, so your net change in position is 0.
Whoa. Okay. That's a huge difference. 10 meters versus 0 meters. That feels like a classic exam trick question.
It is the classic exam trick. Let's use the example from the source material, slightly more complex. Imagine a particle starts at position 6 by dollars. Let's say that's the origin, 0 meters.
Okay, 6 by $1 equals dollars.
Then it moves right to position 6 by 2 tals. Let's say that's plus 5 meters.
Okay, moved 5 meters right.
Then it reverses direction and moves left, stopping finally at position 6 by 3, which is plus 2 meters.
So it went past plus 2 meters on the way back. No, wait. It went 5 meters right, then came back 3 meters left to end at plus 2 meters.
Yeah.
Exactly. Started at 0, went to plus 5, ended at plus 2. Okay, 3 questions. First, what's its final position? Well, it stopped its by 3 to under 3, so plus 2 meters. Perfect. That's just where it is at the end. Second, what's its displacement? Displacement is final minus initial. So 6/3 by $1. That's plus 2 meters, 0 meters. So plus 2 meters. Right again, it ended up 2 meters to the right of where it began. Now the tricky one, what's the distance traveled? Okay. The total walk, first part was from 0 to plus 5 meters. That's a distance of 5 meters.
Yep. Magnitude of the first leg is plus 5 meters. It's 5 meters.
Second part was from plus 5 meters back to plus 2 meters. The change is 225 equals 3 day 3, but distance is always positive, right? So the magnitude is 3 to 5 meters is all in 3 meters.
You got it.
So the total distance is 5 meters plus 3 meters, 8 meters.
Boom. 8 meters total distance traveled, but only plus 2 meters displacement. See the difference?
Yeah, that's really clear now. The distance just kept adding up, but the displacement kind of netted out because of the change in direction, and that leads to the crucial rule, straight from the source. The magnitude of displacement is only equal to the distance traveled if the object never changes direction. The moment it turns around, distance keeps going up, but displacement might start shrinking or even become negative.
Exactly. Nail that difference, and you've dodged the first major pitfall.
Okay. Distance versus displacement. Got it. What's the next conceptual trap? All right, section 2. Instantaneous versus average. This is where we start talking about rates of change speed, velocity, acceleration, and where calculus sometimes peeks in. Uh-oh. Calculus.
Don't panic. Let's break it down. First, let's talk velocity. We already know displacement is the change in position.
Right.
Average velocity is super simple. It's just the total displacement divided by the total time it took.
So in our last example, the displacement was plus 2 meters. If that whole trip took, say, 4 seconds.
Your average velocity would be plus 2 meters, 4 seconds, plus 0.5 meters per second. Easy peasy.
Okay, average velocity is straightforward. Displacement over time. But you said average. That implies there's another kind. There is. And this is the one that usually matters more in physics problems. Instantaneous velocity. Instantaneous, meaning like right now?
Exactly. It's the velocity at one specific moment in time. Think about driving your car. Your average velocity for a whole trip might be 50 miles per hour, but at any given instant, your speedometer might read 60 miles per hour, then 30 miles per hour, then 0 miles per hour at a stoplight.
Okay, so instantaneous velocity is what the speedometer shows at that exact second.
Pretty much. Plus direction, of course. Velocity is still a vector. So plus 70 miles per hour means 70 miles per hour east, maybe, and 70 miles per hour would be 70 miles per hour west.
Right, velocity has direction. And the number part, the 70 mile per hour without the sign, that's just speed. Right?
Got it. Speed is the magnitude of velocity. It's a scalar, always positive, just like distance. Speed is what the speedometer shows. Velocity includes which way you're going.
Okay. Instantaneous velocity is velocity at a moment. Got it. Now,
Yeah.
acceleration.
If velocity is the rate of change of position, then acceleration is simply the rate of change of velocity. It tells you how quickly your velocity is changing.
So how fast you're speeding up or slowing down or
Okay.
changing direction.
Exactly. And again, we usually care about instantaneous acceleration, the acceleration at one precise moment.
Okay, this is where my brain starts to see derivatives and integrals. When do I need calculus, and when can I just use those basic physics formulas I memorized, like $5 equal $V plus at dollar? Excellent question. That's the calculus trap. Here's the simple rule from the sources. If the problem tells you that you have constant acceleration, like gravity problems, where acceleration is always dollars, like Natick $9, 81 millers, $2.
Perfect example. If acceleration is constant, then you can use those simple kinematic equations you memorized. They are your best friends in that situation. Save time, less chance of error.
what if acceleration isn't constant? What if the problem gives me velocity as some function of time, like y due t equals 3t2 plus 2t? The acceleration is definitely changing there.
Ah, you spotted it. As soon as you see position, velocity, or acceleration given as a function of time, or sometimes position, you're in the variable acceleration zone.
And those simple formulas are useless.
Completely useless. You must use calculus. But don't freak out. It's usually basic differentiation or integration.
Okay, walk me through it. How does calculus connect position, velocity, and acceleration?
Think of it like steps on a ladder. Position, velocity,
Yeah.
acceleration. To go down the ladder, find the rate of change, you differentiate with respect to time.
So to get velocity from position.
You differentiate position with respect to time. $V equals dx/dt. Velocity is the slope of the position-time graph at that instant.
And to get acceleration from velocity.
Differentiate velocity with respect to time.
Okay.
And $V is the slope of the velocity-time graph.
Okay. Differentiating goes $6 to V. That makes sense. But what if they give me acceleration, say a act equals 6dt, and ask for the position? I have to go up the ladder. That means integrating.
Yeah, exactly. Integration is how you go A to V, but you're basically summing up all the little changes over time.
But when I integrate, I always get that annoying plus c thing, the constant of integration. What does that mean physically? How do I find it?
Brilliant question. That plus C trips up so many students. It's not just some random math thing. It represents the initial condition of your system.
An initial condition?
Yeah. When you integrate acceleration AT to get velocity VT, you'll get something like 5v text result of integration plus CE. That dollars is the initial velocity, V day. It's the velocity the object already had at the start time, usually T dollars.
Ah. So I need to look in the problem description for something like starts from rest or initial velocity was 5 meters.
Precisely. If it starts from rest, then VDL is 0. If it was already moving at 5 meters, then VDL is 5.5 and C in 5 meters. You need that piece of information from the problem to find the specific velocity function.
Okay. And I guess the same thing happens when I integrate velocity to get position.
Yep. You'll get another constant of integration. Let's call it Solars. That Solars represents the initial position, state dollars. Where was the particle located relative to the origin when the clock started at teacher?
So I need both the starting velocity and the starting position to fully solve these problems using integration.
You absolutely do. If you see functions, think calculus. And if you integrate, immediately hunt for those initial conditions in SHUA $2 in the problem statement to figure out your constants. Without them, your answer is incomplete.
Okay. Calculus trap navigated. Hopefully. What's the third big conceptual mess up?
Deceleration and the sign mystery. This one is all about interpreting those plus and minus signs correctly, especially for acceleration.
Yeah, this gets me sometimes. It's super tempting to see a negative acceleration and just automatically think, oh, it's slowing down.
It's so tempting, but it's often wrong. And it's a classic exam trap. A negative sign on acceleration just tells you the direction the acceleration vector is pointing. In our 1D world, it means pointing left or pointing down. It does not automatically mean braking or slowing down.
Okay, so if negative A doesn't always mean slowing down, how do we know if something is actually slowing down? What's the real rule for deceleration? The key is you have to compare the signs of two things, the velocity and the acceleration at that instant. Compare the signs. Okay, here's the cheat code.
If $1 have the same sign, either both positive or both negative, the object is speeding up. That's true acceleration. The acceleration is helping the velocity.
Same sign, speeding up. Got it. Both positive, moving right, accelerating right, or both negative, moving left, accelerating left. Exactly. Rule 2. If vibe and nuller have opposite signs, one is positive, the other is negative, the object is slowing down. This is deceleration. The acceleration is fighting the velocity. Opposite signs equals slowing down. Deceleration. Okay, it's a clear rule. It's about the relationship between the signs, not just the sign of valor.
Precisely. Once you lock that rule in, these vector sign problems become simple logic checks, not scary math puzzles. Huge confidence booster. Okay, let's test it. Use the classic physics example. I throw a ball straight up in the air. Let's stick with the usual convention. Up is positive, down is negative. Perfect. So as the ball is traveling upwards, right after leaving my hand, what's the sign of its velocity?
It's moving up, so velocity dollars is positive.
Good. And what about its acceleration? What's acting on it?
Gravity. And gravity always pulls down.
Always pulls down. So the acceleration due to gravity is?
Negative. Always negative. Like $9.81 1 meters, $2. Okay. So traveling up. $5 positive, $5 negative. What are the signs? They're opposite.
And what does our rule say about opposite signs?
Opposite signs mean slowing down, deceleration, which makes sense. The ball slows down as it goes up.
Exactly. Gravity is fighting the upward motion. Now the ball reaches the very peak of its flight. What happens right at that tippy-top instant?
It stops for a split second before it starts falling, right? So its velocity is 0.
Bingo. At the exact peak, VDA, critical point.
Oh.
Now, what happens immediately after the peak as it starts falling down? What's the sign of its velocity?
It's moving downwards now, so velocity is negative.
And what's the acceleration still doing?
Gravity doesn't care, it's still pulling down. So acceleration is still negative. Okay, falling down. $8 is negative, $8, and what are the signs? They're the same, both negative.
In our rule for same signs.
Same signs mean is speeding up, acceleration. And yeah, the ball definitely speeds up as it falls.
See, the acceleration sign never changed, but the motion switched from deceleration, slowing down, on the way up to acceleration, speed it up, on the way down, all based on how the velocity sign compared to the constant negative acceleration sign.
Wow, okay, that clicks. Comparing the signs is everything for acceleration, deceleration, not just looking at the sign of S.
Nail that, and you've dodged trap number 3.
All right, these concepts are making more sense broken down like this, but they still feel a bit abstract. Particles, vectors, I hear you. Let's make it super concrete. Time for section 4. The car ride analogy. Okay, I like analogies.
Imagine you're driving a car, but forget turns, forget hills. Just a perfectly straight, flat highway stretching out forever. Pure rectilinear motion.
Got it. Straight road. How do our concepts fit in?
Okay, position. That's like your GPS coordinate, maybe, or like those mile markers on the side of the highway.
Yeah.
It tells you where you are relative to some starting point, say, the city limits sign. That's your origin.
So mile marker 50 east of the sign could be position plus 50 miles.
Exactly. Now, distance traveled. What's that in the car?
The odometer, the thing that tracks total miles driven.
Perfect. That's the total walk. If you drive 100 miles east, realize you forgot your wallet, turn around and drive 50 miles back west.
The odometer shows 150 miles driven. It just added it all up.
Right. That's your distance traveled. But what's your displacement in that scenario?
Started at a sign 0, ended up 50 miles east of the sign, plus 50 miles. Displacement is final minus initial, so plus 50 miles.
Yep. You traveled 150 miles, but your net change in position, your displacement, is only plus 50 miles east.
Okay, that makes the difference clearer again. Now, velocity.
Instantaneous velocity is your speedometer reading right now, plus your direction.
So 70 mile per hour on the speedometer while driving east is $5 is plus 7 to 5 mile per hour.
And if you carefully put it in reverse and back up at 5 mile per hour west,
that'd be $Y in action 5 mile per hour. Got it. Speed plus direction.
Now let's nail the deceleration mystery with the car. You're cruising along, going forward at, say, 60 mile per hour. So velocity is positive.
Okay, $5 plus $60.
You see brake lights way ahead. You slam on your brakes.
Yeah.
What direction does the braking force push, effectively? What direction is the acceleration caused by braking?
Braking opposes motion. So if I'm going forward, positive, the braking acceleration must be backward, negative.
Exactly. Brakes cause a negative acceleration in this case. So you have $5 plus the nanomiler signs. Signs are
opposite.
Which means
deceleration. I slow down. Makes perfect sense.
Okay, tricky scenario now.
Yeah.
You're already backing up slowly, maybe $1 or -5 mile per hour. Negative velocity. You realize you need to stop really fast. You slam the brakes even harder. Brakes still create an acceleration that opposes your current motion. Since you're moving backward, negative, the braking acceleration is...
Wait, so I'm moving negative and brakes oppose motion? The acceleration from the brakes must be in the positive direction.
You got it. So now you have valoration in A plus bubble. What are the signs?
Opposite again.
What happened?
I slow down, even though acceleration is positive.
Yes. You slow down your backward motion. See that, folks? Deceleration is purely about valor, into valor having opposite signs, regardless of whether A itself is positive or negative. The car analogy really helps lock that in.
Yeah, it does. Seeing it with the car makes the sign rules feel much more intuitive. Okay, these analogies and breakdowns are good. What about actual exam strategies, like little tricks or things to look for? Good question. Let's move to section 5. Crucial exam strategies, the aha moments from the source material that can save you time and point. Okay, hit me. Strategy nugget number 1. Recognizing the turning point. We touched on this, but it's vital. In rectilinear motion, when does a particle change direction? Like going from moving right to moving left?
Yeah.
Didn't we say at the peak of the ball's flight the velocity was 0? Is it always $V when it turns around?
Always. For that instantaneous moment when it switches direction, the particle must have 0 velocity. It has to stop before it can reverse.
Okay, V means it's turning around or potentially stopping permanently. Why is that a big exam strategy?
Because problems often ask for things like maximum displacement, farthest point reached, or maximum height. These points almost always occur exactly when the object turns around. So if they ask for the maximum position, my first step should be set the velocity function via 20, solve for the time $t, and that time is when the max position happens. Usually, yes. Find the times when the v goes the year. That tells you when direction changes might occur, which often correspond to max or min positions.
And this links back to the distance versus displacement trap too, right? If I need total distance travel between t80, 10, $10 seconds.
You must first check if v dollars happens anywhere inside that interval, say at t2 40 seconds.
And if it does?
You have to break the calculation. Find the distance from $2 to $2.25, then find the distance from $2.42 to $2t, and add the absolute values magnitudes of those two parts together.
If I just calculate the displacement from $2 to $, I'll get the wrong answer for distance because I missed the turnaround.
Exactly. Skipping the $dollar check is probably the single biggest mistake students make on distance traveled problems. It's a guaranteed point loser.
Okay.
Strategy 1. Check $dollars for turning points and distance calculations. What's strategy 2?
Finding maximum or minimum velocity. Sometimes a problem gives you a complicated velocity function by $v and asks, when is the velocity largest, or what is the minimum velocity?
Okay. How do I find that without just plugging in a million time values?
Think calculus again. How do you find the maximum or minimum of any function?
You take its derivative and set it equal to 0.
Right. And what's the derivative of velocity with respect to time?
Acceleration.
Bingo. So the condition for maximum or minimum velocity is when the acceleration is 0. Find the times when $, then plug those specific times back into the original $v function to find the max or min velocities.
Okay, that's clever. $1 for maximum position, $8 for maximum velocity. That's a good shortcut. Strategy 3.
Strategy 3 is more about recognizing the type of problem you're facing because the solution method changes drastically. We've really covered two main types already.
Constant acceleration and variable acceleration. Yep. Constant A means use the simple kinematic formulas. Variable A, given as a function, means use calculus, differentiation integration. But there's a third flavor mentioned in the sources, dependent or relative motion. Relative motion, like how fast car A is moving compared to car B.
Exactly. It's when you have two or more objects and you need to describe the motion of one as seen from the perspective of the other.
How does that work in our simple 1D world?
In 1D, it's usually just straightforward vector subtraction. If you want the position of object B relative to object A, written vex BA, you just calculate vex B at vex A.
So if car A is at plus 50 meters and car B is at plus 70 meters on the same road.
The position of B relative to A is vex A plus 50, plus 20 meters. Car B is 20 meters ahead of car A. Same logic applies to relative velocity and relative acceleration.
Seems simple enough in 1D, just subtract.
It is, conceptually. It gets math-heavy if they accelerate differently, or if, as the sources hint, the motion becomes 2D later on, like car A going north and car B going east. Then you're subtracting vectors with vec-i and vec-i components.
Yeah, the source mentioned a result like $60 vec-i, 13.4 vec-meters for relative position in 2D. Looks messy.
It can be. But for your typical rectilinear motion exam, focus on recognizing when it's a relative motion problem, comparing two objects, and remember the core idea is subtraction, even if it's just simple 1D subtraction for now.
Okay. Constant A, variable A, relative motion. Check $, check otter. Those are solid strategies.
Yeah, understanding those distinctions and checks can really streamline your problem-solving approach.
All right. This has actually been helpful, like demystifying some of the jargon.
Awesome. That was the goal. Let's just quickly recap the absolute must-knows, the core of the cheat code.
Okay, summary time. We hit the 3 big traps. Trap 1, distance versus displacement. Remember the total walk, scalar distance, always adds up, versus the straight shot, vector displacement, final minus initial. And they're only equal in magnitude if the object never turns around.
Instantaneous versus average rates. Average is simple, total change, total time. Instantaneous is at one specific moment, and if variables are given as functions, you got to use calculus and remember those initial conditions, fix $v for the integration constants.
Right. $6 left right haro, v left right haro, $8 via differentiation and integration. And trap 3, the sign mystery. Don't assume negative acceleration means slowing down. It's all about comparing the signs of vine and a dollars. Same sign as speeding up. Opposite signs equal slowing down, deceleration. The sign comparison is key. Okay, so if I'm cramming tonight, what's the one single thing I should focus on? The most immediate, actionable step? Great question. Based on common mistakes, I'd say focus on trap 1. Distance versus displacement. Specifically, the calculation part was the action step before you solve any problem that asks for total distance traveled over some time interval, SOP. first step. Set the velocity equal to 0 and solve for time $t. See if any of those times fall within the interval the problem cares about. Check for turnarounds inside the time window.
Yes. If there is turnaround time in there, you absolutely must break your distance calculation into separate segments before and after the turnaround. Calculate the magnitude of displacement for each segment and then add those positive magnitudes together.
Don't just calculate the overall displacement and call it distance. Do the $V check first.
That single check will save you so many points. It's the #1 killer on these exams. Nail that check every single time.
Okay, check V $30 for distance problems.
Yes.
Got it. So what does all this mean in the bigger picture? Why grapple with these concepts? Kinematics, even simple rectilinear motion, teaches us something fundamental. Movement isn't just about the destination. The path matters, literally, for distance.
Exactly. And think about this. If you can really master motion in a straight line, you've actually conquered half the battle for understanding motion along a curved path, which is called curvilinear motion.
How so?
Well, the source material mentions that for curved paths, velocity is always tangential. It follows the curve. That's kind of like our straight line velocity. But the acceleration on a curve, it's more complex. It has 2 parts. One part points along the path, changing the speed, like our rectilinear acceleration. But there's another part pointing towards the center of the curve, making the object actually turn.
So nailing the straight line acceleration helps understand at least one piece of the curvy stuff later.
Precisely. If you get the rules for speed changes here, you're halfway to understanding more complex motion. Something to think about. After you crush this exam, of course.
Okay, feeling a bit better about this now. Time to hit the books with these strategies.
Go for it. Use this cheat code. You absolutely got this.